This is the third of 3 videos from Chapter 6 review. And this one is for upper level charts. And to get right into it, upper level charts are charts that cover the lowest 10 kilometers of our atmosphere, where 90% of our air is. And if you look at the entire atmosphere, that's a very, very small altitude in comparison to our entire atmosphere. But it is enormously important because of the density of the air that is associated with those lowest 10 kilometers. And in fact, if you look at 5 kilometers up, you are seeing that you have 50% of the air in the atmosphere below you. We call that level at about 5 kilometers up a 500 millibar level. The surface level is at 1,000 millibars. At about 5 kilometers, you have about 500 millibars. When we're going to be studying these upper level charts and introducing them to you, this review looks at the 850 millibar charts. And this is simply a review. So if you need to go back over this, then you need to go into the videos that are in the Chapter 6 folder in Blackboard and in my YouTube channel under Chapter 6. As you recall, an upper level chart is like a topographical map for air pressure. And when you have an 850 millibar chart that you're looking at, the man or the woman in that graphic on top is feeling that 850 millibars above him or her and pressing down upon them. They're not at surface level where there's 1,000 millibars pressing down on them. They're at a higher elevation. When they're in Florida, that elevation that they're standing on is higher. Because Florida air is warmer, it's less dense, and it can rise to a higher elevation. When they're at the North Pole, that elevation at 850 millibars is much lower because the air is much more dense. As a result, that warm air can form ridges in our atmospheric maps, or the cold air can form troughs in our atmospheric maps. And this is the important thing. Those upper level maps, everyone is at the same pressure with different altitudes for that pressure, as opposed to the surface maps where everyone is at sea level pressure because we alter all the sea levels throughout the world. We alter all of the altitudes throughout the world to sea level in order to understand the horizontal movement of air at the surface. It turns out that there's such a change in pressure between even sea level and 30 stories up in a skyscraper. Think of Manhattan. There's such a change in that pressure between those 2 points that it could really be the same pressure change that you would notice between Florida and New York. We really can't understand weather with those differentials in there. So we put everybody in a surface map on a level playing field. And we put everybody on an upper level map on a level playing field for the same pressure. Upper level maps, contour lines, topographical. Surface maps, isobars instead. Review that if you need to. We also know that on upper level maps, the winds are parallel to the contour lines. They don't go across the isobars because there are no isobars on upper level maps. There are contour lines on upper level maps. And you may wonder why you're noticing the winds parallel to the contour lines. You should go back over this on the other videos. But to review quickly, you know that the pressure gradient force is the most powerful force when it comes to winds, but it is deflected to the right by the Coriolis force, which really picks up its power as the wind speed increases. When the wind speed increases to a speed that is so fast that the Coriolis force can balance the pressure gradient force, the wind direction is the net force that rides between those two opposing forces. The wind is the net force. So go over that material, and you can look back on this video as well. Finally, at position 5, where the pressure gradient force is balanced by the Coriolis force, we no longer have a change in direction. And remember, a vector is dependent on speed and direction. When we're measuring force on this vector, we measure force as equal to mass times acceleration. If we're no longer changing that acceleration with speed or direction, then our acceleration is going to equal 0. When you put that 0 into the force equals mass times acceleration equation, you'll wind up that the net force of that wind at that position 5 is going to be 0. It seems a little counterintuitive, but that wind is known as a geostrophic wind. That geostrophic wind then goes parallel to the contour lines, usually in a westerly direction. Go back over this if you need to review it in the other videos and in the other PDFs. There are types of geostrophic winds. There are zonal geostrophic winds that go from west to east. And they tend to clear out the surface storms very rapidly, particularly in the eastern half of the United States. There are also meridional, tough to say that, winds that follow the north-south meridians of longitude. Those winds are often found right before the Rocky Mountains, and they intensify surface storms rapidly because they actually are very fast-moving winds, but they divert the air to slow down the westerly movement of air in that area. So they give time for these surface storms to intensify. There are different speeds that are associated with these directional winds. When you see the gradients in gray there of the contour lines that are very tight, and we're looking at the gray lines here, when those gray lines are tight for the contour lines, you're going to be having faster speeds aloft, much like you would notice for isobars. Because remember in our description, back in the other videos, that these are essentially horizontal wind patterns that are going across altitudes. So if you need to review that, go back over the other videos. But tighter contour lines, higher speeds aloft. And conversely, broader contour lines, and these are more gentler speeds aloft. You will notice it down there, right in near the Gulf of Mexico. And to review that, it's a little bit simpler to review it in the gentler winds than it is with the more intense winds. But to review it generally, you are looking at the altitude for 500 millibars pressure above you at 5,880 meters in that case, and at 5,820 meters. What you're saying is that 500 millibars of pressure is at 5,880 meters off of Cuba or so, and that 500 millibars of pressure is lower around Louisiana and Texas. So the same altitude at 5,880 meters in Louisiana, Texas, probably has lower pressure of 450, 400, and you are actually working on a horizontal pressure gradient force along that altitude of 5,880. Again, review this if you need to. It's covered more in depth in my other videos. And just as an aside, the red dotted lines in here are not contour lines. They are isotherms, which is another thing that you should remember in order to use the vocabulary that you need for atmospheric science. Now, how can you know whether or not this is a zonal or a meridional pattern? How can you know the atmospheric wind direction? Looking at the cloud movement will really help you to do this. And with a little logic, you can figure out where the low pressure systems are aloft, up in the atmosphere, where the high pressure systems are. When you move with the cloud direction that you see, particularly the cloud direction that you see highest, you are moving with the low to the left. Let's understand why that is. You're moving with the low to the left because you know that winds at the upper levels tend to cross the isobars and deflect to the right, and tend to go parallel with the contour lines. That atmospheric low pressure system that you see highlighted there means that there is less pressure above that altitude. In other words, the winds at the upper levels were crossing the contour lines and going from high to low and deflecting to the right. And you know that the low pressure system atmospherically means there's less pressure above that altitude, meaning that it's susceptible to getting an atmospheric high to fill in from the west and dump air molecules into that atmospheric low. Dumping air molecules into that atmospheric low means that you increase the density and cause sinking. And in causing sinking, you're causing that low cold trough. You're causing that sinking air. I hope this helps you. If you have any questions, put the questions underneath in the comments section in YouTube, and then I can get back to you and address them. If you have any questions about any of this, this is in the book in Chapter 6, or you can look through the review videos and the PDFs. Good luck.